Now, let's talk for a minute about scalar multiplication. So when you scale something, what do? So if you made a scale model of a car, what are you doing? Yeah, usually it's shrinking, but yeah, stretching or shrinking it, but keeping all of the relative lengths proportional. So scalar multiplication, well, what we want to happen when we multiply a vector by a number, say 2, we would like to make an arrow essentially that's twice as long, headed in the same direction, but twice as long as the original. So let's start with that kind of visual definition as our guide. So let me draw in to kind of convince you of where scalar multiplication comes from symbolically. Let's start geometrically. And let me go ahead and draw an arrow. Okay, so let's say we start with this vector right here. And let's say I want to create a vector that's twice as long. So let's give this vector a name. Let's call it V. And now I want to create a vector 2 times V. And here's what I want to happen. I want to make a vector. So let me use a different color here. Let me use red. I want to create a vector that is, and I'm just doing this visually so it won't be perfect, that goes in the same direction as V, but twice as long. That looks about twice as long. I might be a little off on that, but close enough. So I'm going to say that this vector right here is 2 times V. And you can see they're parallel, so they head in the same direction, right? Yeah. Now, okay, that's all fine visually, right? You can really wrap your brain around that. But what would that mean symbolically when you represent a vector in component form? So let's say that this vector V, we can represent it with components, let's just use A and B for simplicity. So instead of using, and you'll see me do this a lot, instead of using delta x and delta y, I'm going to say delta x is A and delta y is B just for convenience. It's easier symbolism. Well, okay. Then how could we get twice V in component form? Okay, those of you that know the answer, what do? You'd multiply A by 2 and you'd multiply B by 2. So the component form would be 2A comma 2B. But some of you have never seen vectors before, so let's give that some justification here based on our visual or geometric definition of scalar multiplication. So I'm going to put this copy of 2V right on top of V. And now I can really adjust it so it looks like it's twice as big. Okay. And I'm going to create, surprise, surprise, a right triangle. Okay, hopefully it's not a surprise. It is trigonometry, after all, that we're studying right now. So I'm going to create 2 right triangles, actually. I'm going to create the one corresponding to, if I dropped a perpendicular from the tip of V, like so, I'm going to create that right triangle. And I'm going to create the right triangle I get when I drop a perpendicular from the tip of 2V. Like so. So that the big triangle that you see, the big right triangle that you see, kind of encompasses the triangle formed by V in the perpendicular and the horizontal side that I drew. And so that this side here is, of course, parallel to this side, because they're both dropping perpendiculars from parallel lines, parallel vectors. Okay. So here's the thing then. In this smaller triangle here, let me zoom in on this. In this smaller triangle here, then this adjacent side to this tip, well, it's really the tail of V. This adjacent side then, according to my labeling, has length A. I'll be consistent with my coloring, so it has length A. And that horizontal side has length A, and the vertical side has length B. And the hypotenuse, now let me move some of this stuff out of the way. Okay, now this hypotenuse then from of just V then has a certain length associated with it as well. And of course, you can get that length using the Pythagorean theorem, but let's just give it a name, C. Then, by the way we've created this geometric definition of scalar multiplication, what's the length of the big hypotenuse for 2V? It's 2C, right? Yeah. So the length of the hypotenuse of the bigger triangle then has just got to be 2C. But we know from geometry that the big triangle, I'll write this down using very very unmathy notation. The big triangle, well, that's a little bit mathy. So the big triangle is similar to the little triangle. What that means is corresponding sides are proportional. And there is a constant of proportionality, which has to be 2. Once you find it for one side, it stays the same for all the sides. The constant of proportionality is 2 and is the same for all sides. That's what it means to be a similar triangle, right? And is the same for all corresponding sides, which simply means then that the horizontal side of the big triangle has to be twice A. And the vertical side of the big triangle has to be twice B. But wait a minute, this is the horizontal component of 2V, the vector 2V. This is the vertical component of the vector 2V. So that's it. I mean, visually we've shown how we should perform scalar multiplication symbolically, right? So the conclusion is this. So component-wise, 2V, it has components 2A and 2B. So then that gives us kind of a guide as to how to proceed generally for the definition of scalar multiplication symbolically. If you have a vector V, and I'll go back to my my component form delta x, delta y here. Hopefully that doesn't bother you. So if you have a component form of V, delta x, delta y, and let C be a scalar. Well, wait a minute. I'm kind of introducing a definition here. Think of a scalar as a single numerical quantity. Okay. Then, this is the big definition we're trying to come up with. C times V, you guys have kind of already told me, has to be, what do? You take C times the individual components, delta x and delta y, right? To get the component form of C times V. So it equals C times delta x, comma C times delta y. Does that make sense to you? Not too crazy, right? Let's suppose you're given a vector V. Then what does, note number one, what does K times V look like? K times V is a vector that is, well, we got to be careful here because we don't know if K is negative or positive, do we? So we're assuming K is a constant. K times V is a vector that is, let's say, absolute value of K times as long as V. And if K is positive, then K times V will point in the same direction as V. And if K is negative, it'll point 180 degrees from that. It'll point in the opposite direction. So we'll make the first note that k times v has length absolute value of k times that of v. Does that sentence make sense to you? K times v has length absolute value of k times that of v, the length of v, in other words. And then we should say this: if k is greater than 0, k times v points in the same direction as v. And note number 3, if k is less than 0, then it points in the opposite direction. Then k times v points in the opposite direction as v.